Graph each of the functions. All right, let's talk about the function I'm going to call g of x here, which is going to be written as 1 over x. This is sort of a very basic rational function, and if I were to actually draw that rational function, you might be familiar with the way this function looks. It's actually kind of like this kind of swooping figure here, and then another one in quadrant 3. Okay, so there it is, and basically the graph points through the location 1, comma 1, right? There's a point there, and there's also a point over here at -1, comma -1, right? Because if you plug those values into that function, you get the results out, right? So g of 1 is equal to 1, and g of -1 is equal to -1. Okay, so that's that original basic rational function. If we know what that looks like, then what we can tell they've done here for this function f of x is they've basically added that 1 to it, right? Which is the same as putting that at the other end. In other words, it's a transformation that just moves the whole function up one step, right? So everything in the graph will be moved up one step. So one thing I want to mention about this original function that I call g of x here, that function has a horizontal asymptote here on the x-axis, right? Notice the graph kind of hugs that without crossing it, right? It also has a vertical asymptote here at the y-axis. Now basically what's going to happen when we shift this function up to graph the function capital F of x, we're basically going to just move up that asymptote, the horizontal one, up 1 unit higher. The vertical asymptote will not be affected by that transformation. So let's go ahead and graph capital F of x here. Again, remember that horizontal asymptote will now move up one step. So instead of being along the x-axis, we're going to move it up to the location where y is equal to 1, right? So instead of y equals 0, it moves up to y equals 1. And the original point we had that we had indicated, the 1, 1 point, is going to move up by 1, so it'll be at 1, 2 now. So we'll have that point located here. And that graph will hug this horizontal asymptote and still hug the vertical asymptote that it hugged before. Now, instead of having this point here, -1, -1, we're going to add 1 to that, so it'll be -1, 0. So that means that point occurs here, but it'll still hug that horizontal asymptote, right? And hug this one here as well. Okay, so that's basically what the graph looks like. So it's very similar to the graph I call g of x, except for we've moved everything up just one step, right? Still has a horizontal and vertical asymptote. It's just the location of the horizontal asymptote has been shifted up 1 unit because the whole graph has been shifted up 1 unit. But that's it. All right, let's take a look then at the next function, the function b, and see how to graph that one. Well, to graph that one, it might be worthwhile to look at another classic function. All right, so let's call little f of x here equal to 1 over x squared. That graph kind of looks like this. Okay, so what the graph is doing is it's basically hugging the x-axis and hugging the y-axis, and it has these two swoops in the upper half of the rectangular coordinate system. So that's essentially what 1 over x squared looks like. That's what this graph looks like. So in g of x, all they're doing is basically transforming that, right? So if you think about what they're doing, they've added 2 to it. That's going to shift the whole graph up 2 units, right? So this plus 2 is going to move the whole graph up 2 units. That'll move that horizontal asymptote here in our drawing up by 2 units. Then they also have subtracted 1 inside this parenthesis here. Remember what happens when you do something like subtracting 1 inside the parenthesis. It actually moves it in the opposite direction of what you would think. It's going to move to either left or right when you put something in the parenthesis like that, but because here everything's opposite of what you would think, -1 would normally you would think of moving to the left by 1. Here it's going to be moving to the right by 1. So it's going to shift the graph over to the right by 1. And then finally, we have this 2 on top. Instead of having a 1 on top, they put a 2 on top. What that does is basically cause a slight stretching, which means the points rise a little more rapidly, but they're still anchored sort of along that asymptote. So let's try to put all those things together. So I'm going to raise the asymptote up by 2 units here. Instead of being along the x-axis, I'm going to say it's going to come across here at y is equal to 2. So that's where that will occur. And instead of being sort of surrounding this part here like we did before, we're going to move that over by 1 because of this -1 that we see here, right? It's going to move that over by 1 unit to the right. So we're going to have the graph actually hug this position, right? Now, that means there's a shift in where the vertical asymptote is located. Instead of being along the y-axis, it's located one step to the right of that, where x is equal to 1. And then finally, we just need to sort of take care of the 2 part on top of this function here. In order to compensate for that, it might be worthwhile just to plot one distinct point. For example, I want to know what's going to happen when x is equal to 2. So what happens when x is 2? Well, if I plug in 2, I'll end up with the idea that we have 2 plus 2 over 2 minus 1 squared, right? That'll be 2 plus 2 over 2 minus 1, which is just 1 quantity squared, or in other words, 2 plus 2, because 1 squared is 1, divided into 2 gives you 2, so 2 plus 2, or in other words, 4. So the y-coordinate becomes 4. So that means at this location, we're going to go 1, 2, 3, 4. We have a point there. What happens when x equals 0? Well, when x equals 0, we'll end up with 2 plus 2 over 0 minus 1 squared, which is going to give you 2 plus 2 over negative 1 squared, which is the same again as 4 because it'll be 2 plus 2 over 1. So in other words, 4 is the answer again. So at 0, you have the point 4. Now let's continue with that idea. Let's go ahead and move 1 to the right of that original point 2, 4. So we're going to now use the point 3. So we'll have 2 plus 2 over 3 minus 1 squared. That's going to be the same as 2 plus 2 over 2 squared. And that'll be the same as 2.5 because 2 squared is 4, 2 over 4 is 1/2, so 2.5. So we're going to say 2.5 goes here. So just like we went 1 to the right of 2, we're going to go 1 to the left of 0 here to do negative 1. Let's see what happens when we plug negative 1 into the function. So you plug negative 1 in the function, you get 2 plus 2 over negative 1 minus 1 squared. That's the same as 2 plus 2 over negative 2 squared. And that's the same as 2 plus 2 over 4. So again, 2.5. All right, so let's plot these remaining 2 points. At 3, 2.5, so 1, 2, 3, and then 2.5, 1, 2 here. And then we do the same thing on the other side, at negative 1, 2.5. All right, so when we connect these, we get that same hugging effect we said before, right? Hugging the line, the asymptotes there. But now we know roughly where those are located, right? By putting a couple of points on the graph, makes the graph look better. Okay, so we basically did some transformations and we plotted a few points just to make it more detailed. You didn't actually need the points. You could have just plotted it by hand and said it's approximately there, but now at least have a rough idea of where the graph is. Okay. All right, let's take a look at example C. To do example C, actually, it looks a little complicated at first, but really all you need to do here is to divide this x squared into each of the pieces here. So you got to look for these things when you're looking at it. If it doesn't look anything like a simple function that you're used to working with, you might want to try to manipulate it a little bit algebraically. You might have thought to factor the numerator, but then it would be like doing, x minus 1, x plus 1 over x squared, and that doesn't seem very helpful. But instead, if I just take the simple step of dividing x squared into both terms separately, I'll be able to rewrite the function in a way that's going to look a lot more useful. So what this is going to do is give us r of x is equal to x squared over x squared minus 1 over x squared. And that's useful because that just simply becomes 1 minus 1 over x squared. If I were to rewrite that in another way still, I could say that that's r of x equals to negative 1 over x squared plus 1. I just switched around the locations of these two terms, right? And now what we can see is that, hey, this part is very much like this graph, except for the negative out in front, and then they put a plus 1 at the end. So all they're doing is inverting the graph, they're reflecting it across the x-axis, and then they're moving it up 1 unit. So basically, they're going to take our original graph, right, and they're going to move it up 1 unit. That means the horizontal axis is going to shift up off the x-axis by 1. So it means we're going to end up with a new horizontal asymptote up here, where y is equal to 1. We're still going to have that vertical asymptote where we had it before. And that would basically have made the graph look like this, right? It would have been something like this, essentially. Except for one small detail. The negative in front of that piece makes that reflect across that horizontal asymptote. So it means the graph is actually going to hug it this way instead. So it's still hugging the horizontal asymptote, but it's just doing it in the lower half now instead of the upper half of the rectangular coordinate system. So basically that's the graph of r of x. So we didn't even have to plot a point. We could just see that it's basically the same as the function that we had over here that we called lowercase f of x, but we have to invert it and then move it up 1 unit along the y-axis.